Okay, let's take a look at heat some more. Heat is a very important concept in weather. And last time we were taking a look at heat transfer by conduction, convection, radiation. We talked about how conduction is probably the least important of the three methods of heat transfer. Let's take a look at factors that affect the amount or rate of heating for the Earth. Okay, so a major one is the angle of insolation. And we talked about this word in one of the other videos, insolation. If you remember back to that, it stands for incoming solar radiation. So incoming solar radiation. So the angle and duration of insolation, which largely depends on, well, two things. Where you are on the world, latitude. If you live near the poles, you're always, no matter what time of year, going to have a low angle of insolation, or maybe none, like in this example, you're at the South Pole. And the season. We, of course, have a higher angle to the sun and more duration, more light, a longer day in the summer, and, as you know, short days in the winter, right? So that certainly is a major factor in our weather. Some of these things you probably know, and maybe some of them you don't. But there's land versus water. Land heats faster, and water heats slower. Now, there's a concept in physics called specific heat. And if you take out your reference table and take a look at the cover, over here is a table of specific heats of common materials. Well, the physics of it and the equations of it really aren't terribly important for us here. But basically, the concept is high numbers, like water, are materials that heat slow, and they also cool slowly too. So specific heat is a measurement of how quickly materials heat up and how quickly they cool down. And what's a little different about specific heat is big numbers mean it's slow. So water takes a long time to heat up. Back when we talked about hurricane season is in the late summer, early fall, because it took all summer long for the ocean to heat up. We also see this when you just simply boil a pot of water on the stove. If you go to make spaghetti, well, it's an easy dinner to make, or macaroni and cheese or something like that. But it might take as long as 20 minutes for that pot of water to come to a boil. It takes some time. It doesn't happen right away. And if you were to switch that stove off and let the hot water cool down to room temperature, it might take hours for all of that heat energy to slowly get transferred back out into the kitchen. So water has a very, very high specific heat, which means it heats slowly and it cools down slowly. If we look at this list, other materials are faster. And if we look at the metals especially, iron, copper, and lead, very low specific heats, these are fast to heat up and also to cool. Very nice pots and pans are made out of copper. A really good frying pan is sometimes made out of copper because copper has a very low specific heat. It heats up quickly, it cools down quickly, responds to temperature changes really well. So if you start burning your food, you can turn the temperature down and the pan's going to cool down with that flame or heat source. If you need to get it hotter, it'll heat up really fast. An iron frying pan takes more time to heat up. It takes longer to get hot, and then once it is hot, it's going to take longer to cool off. And that's the idea of specific heat. So you don't really have to worry about the equations here or anything like that, but the concept is something that you need to be aware of. Okay, so if we go back to this, land. Oh, and by the way, if we look at rocks like granite and basalt, much lower specific heat than water. And this is why land heats up faster and water heats up slower. If we measure the specific heats, land, no matter what rock or material it's made from, is almost always going to heat up faster than water. Water has that very high specific heat. I'm sure you've learned about in the past color. Dark materials versus light materials. And dark materials, of course, heat faster. You've probably felt that if you wear like a black t-shirt or black pants on a hot day. So dark materials heat faster. Light reflects more. Light-colored objects reflect more energy. Reflects more energy. And something that a lot of people don't realize is also the nature of the surface matters too. Smooth versus rough. A rough surface absorbs more energy and it heats faster. A smooth surface will heat slower. And the reason why has to do with reflection. When light hits a smooth surface, it basically all bounces off, or most of it bounces off that smooth surface, and it gets reflected away from the object. But when we have a rough surface, when the light comes down and hits a rough surface, a lot of it gets absorbed and it doesn't reflect back as well. So less gets reflected, less light or radiation gets reflected off the object. So rough surfaces absorb more energy, heat faster, because they're not reflecting as much energy off their surface. That brings us back to field maps. Now, we did field maps back in September. I know that maybe it wasn't everybody's favorite thing, but I warned you that they would be back, and they are back. So field maps are very important for weather. We can use field maps to map just about every weather variable. We can make a field map of temperature, like in this example. We can make a field map of humidity, precipitation, air pressure, snowfall in inches, snowfall in centimeters, rainfall, and everything you can think of. Hail strikes, thunderstorms, lightning, all kinds of variables. So when we're dealing with temperature, and you might remember this from back in September, ISO lines are lines that connect points of equal value. When they're specific to temperature, we call them isotherms. So these are points, or lines that connect points of equal temperature. Now if we look at this map shows temperatures that were taken at various cities around the country. And one of the things that we'll talk about later in the unit are these circles. These circles are something called station models. A station model represents a weather station. So that circle on the map represents a weather station that's physically on the ground. The weather station we have on the roof of the school would be drawn this way with a circle. There's many, many symbols that go along with the station model. These are simplified just to make it a little easier for you to look at. And right now they're only showing really, as far as I can see it, two variables. Temperature in the upper left in Fahrenheit. And then also sky cover. Sky cover would be how cloudy it is. And if the circle is shaded in, that means it's very cloudy. If it's an open circle, it means the skies are clear. Where there's an R in the center, that means, of course, it's raining. So here it says to draw isotherms at 30, 40, 50, 60, 70, and 80. So we can go ahead and do that. And we've been doing that since September. It might be a little while since we've done it. So, not a bad idea, a good idea actually, would be to maybe pause the video here, go ahead and do this. And I'm going to pause it too, and do it, and then show you what it looks like. Save a little bit of time that way. Okay, so here's my completed map. Hopefully yours looks the same. Almost made a couple mistakes, and I know I was being a little lazy here. I probably should have used a pencil, but I just had a pen and just honestly didn't feel like looking for one. But I almost made a little mistake right here. And here's my 40 line, and I almost went this way and then caught myself and came down this way. Yeah, but here's the map. Check yourself. Make sure your map looks the same. Some of these spots are easy to make little mistakes. And don't forget the little 80 line down here. and I ran it off the edge or drew an incomplete line because we don't have the whole map. But this is a map of temperature. And when we look at it, we can see that overall, the isotherms are going horizontally. They, of course, curve, but more or less, they're going horizontally down the country. And that makes sense because it's colder in the north and it's warmer in the south. So it makes sense that the isotherms are going horizontally across the country, more or less. And, you know, they don't go completely horizontally because there are times where maybe it's a little hotter in some place or a little colder in another. It's air moves around. But in general, we have horizontal lines. Now, back in September, we also talked about this idea of gradient. And we calculated the gradient between different points, and we basically thought of it as slope. How steep a slope was, how steep a mountain was, how steep a valley was. Well, it's a similar idea with temperature. We can calculate a temperature gradient. And this is where the temperature changes the most. I'll say the greatest temperature change over the least distance. Or that's what we're looking for when we're looking for the greatest temperature gradient. So to find the greatest temperature gradient, we don't even have to do any math. We could, but we could just look at it. And where the isotherms are really close together, that means that we have a really extreme change in temperature over a short distance. And if we look to the cities of Richmond and Hatteras, well, here's 45 degrees, there's 68. And in a relatively short distance, we have a significant change in temperature. Nowhere else on the map do we have such a big change in temperature over such a short distance. So that would be Richmond and Hatteras. And this is again because the isotherms are close together. If we wanted to actually calculate the gradient, we could do that between two cities like Cincinnati and Chicago. And to do that, well, here's Cincinnati and there's Chicago. And we need to, if you remember, gradient, the formula for it was change in field value over distance. Well, in this case, my field value is temperature in Fahrenheit. And if we look at the map, Chicago has a temperature of 40, and Cincinnati a temperature of 60. So I have 60 degrees Fahrenheit minus 40 degrees Fahrenheit divided by the distance. Now the only trick here is that you have to use a ruler and get the scale miles. Remember, there's a scale, a bar scale in the lower corner of the map. Or another way of doing this is to just simply take some scrap paper and line the edge up with the two cities. There's Chicago and Cincinnati. There and there. And I could take my two marks. This isn't as accurate as with a ruler, but it'll work. And I'll put it down here against my bar scale. And line the first mark up with 0. This way. And that puts me up with approximately 250. So that means that the distance between the two cities is roughly 250 miles. And if I go to get my gradient, now I'm going to put 250 miles down here. And when I subtract, of course, I get 20. And then if I divide by 250, well, 20 degrees Fahrenheit divided by 250 miles. When I divide, I get 0.08. And now we run into the problem of the units. What would the unit be? Well, we have Fahrenheit up here. We have miles here. So I'm going to do Fahrenheit, degrees Fahrenheit per mile. And this means that if you got in your car and drove a mile, every mile you drove, the temperature would change by 0.08 degrees Fahrenheit. Okay, so that's all for now. I'll try to get some more videos out soon. Okay, thanks.